Just as motion can alter our perception, according to special relativity, time in certain areas is also affected by gravity. Where gravity is especially intense, time flows at a slower rate than in areas with weaker gravity. So, if you were standing near a massive object like a black hole, your clock would move at a slower rate than one placed farther away from this massive mass. General relativity introduces the idea of black holes, which are regions where gravity is so powerful that not even light can escape. The boundary surrounding a black hole is called the event horizon, and it marks a point of no return. Once an object crosses this boundary, it is drawn into the black hole without any possibility of getting out. Einstein's theory of relativity has profound implications for the structure of the universe. Initially, he added the term cosmological constant to his equations because he believed the universe was static. However, upon discovering that the universe is expanding, he referred to this as a great mistake. The idea of an expanding universe, based on general relativity, is central to the Big Bang theory, which describes the universe's beginnings. Another important idea of general relativity is gravitational waves. These are ripples in the fabric of space and time caused by extremely massive objects moving quickly, such as black hole mergers or neutron star collisions. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, LIGO, directly detected gravitational waves, providing further proof for Einstein's theory. Over time, scientists have conducted numerous tests to validate general relativity, and each time the theory has proven to be accurate. Whether by observing planetary motion, light bending, or the detection of gravitational waves, general relativity continues to be a solid and trustworthy framework. The assertion that gravity is a myth may sound startling, especially since we experience it every day. However, in the field of physics, it's normal to challenge and reconsider established theories. Scientists like Brian regularly challenge established wisdom. In the domain of gravity, some alternative perspectives exist. One such theory, modified Newtonian dynamics, MOND, suggests that gravity behaves differently at low velocities, particularly in galaxies, without needing to use dark matter. Rather than positing invisible matter, MOND suggests that gravity strengthens at slow speeds. The debate on gravity also involves the enigmatic concepts of dark matter and dark energy, which were introduced to explain certain cosmic phenomena. Critics argue that these ideas may be unnecessary and that alternative explanations could account for what we observe. Some scientists who oppose Einstein's theory of gravity explore new possibilities, such as theories involving unknown particles or forces that could alter or enhance our understanding of gravity. It's important to recognize that in science, new ideas are not dismissed outright. Instead, they undergo rigorous testing to determine whether they hold up. For instance, Einstein's concept of time as part of a four-dimensional continuum, where time travel may be limited by the speed of light, has been creatively explored alongside ideas such as wormholes and shortcuts. Stephen Hawking's chronology protection conjecture suggests that travel into the past is unlikely from a physics standpoint. Ongoing experiments and observations aim to ascertain whether these new theories can explain phenomena like gravity in a way that aligns with our current understanding. While many ideas have been considered, none have successfully replaced the gravity laws that have been around for a long time. Questioning and rethinking established theories is a crucial component of scientific progress, fostering further research and a deeper understanding of the universe. Within the field of gravity, general relativity continues to be the most significant and successful theory. Despite challenges and competing ideas, it consistently performs well in experiments and explains various phenomena, such as planetary motion and the bending of light around massive objects. General relativity endures because it is both simple and capable of accommodating a wide array of phenomena. As previously discussed, Einstein's special theory of relativity suggests that time can behave differently depending on your speed. Now, let's explore how this idea affects real-life scenarios, particularly in space exploration. Space exploration is exciting but challenging because space is vast. According to Einstein's theory, the fastest possible speed is that of light. This makes traveling between stars a major challenge, even with advanced technology, due to the long travel times required to reach even the closest stars. To understand what happens to time when traveling in space, Consider the famous twin paradox. Picture this. One twin remains on Earth, while the other embarks on a fast journey to a distant star. When the space-traveling twin returns, they find that less time has passed for them than for the twin on Earth. In essence, they have traveled into the future. Time is critical for space travelers because the longer the trip, the more time slows down. If astronauts were to visit nearby stars, where time slows down considerably, they would age more slowly than people on Earth. While this may seem like science fiction, it's a real effect predicted by relativity. Imagine humans sending a crew to a distant star system. Due to the vast distance, the journey could span many years. Even though the astronauts would be traveling quickly, they would experience time more slowly because of the time dilation effect. However, from Earth's perspective, much more time would pass. Time dilation affects not just living beings but also technology. Computers and communication devices on spacecraft must account for time dilation for high-speed, accurate space travel. High speeds bring physical challenges such as isolation, exposure to cosmic radiation, and the psychological toll of being far from Earth for an extended period. In our everyday lives, we can observe time dilation effects in the Global Positioning System, GPS. GPS depends on the precise timing of signals from moving satellites. Because these satellites experience time dilation, it is important to account for these effects for accurate GPS readings. Neglecting this would lead to substantial errors in navigation. Now let's look at why time only flows in one direction. Time governs our lives, moving from the past to the present and into the future. This one-way passage of time is fundamental to our reality. But why does time have this one-way nature? To understand this, we turn to the concept of entropy, a measure of disorder or randomness in a system. Entropy, which is tied to the arrow of time, tends to increase as time passes, driving time to move in one direction. This principle is encapsulated in the second law of thermodynamics. This relationship expresses that in any closed system, total entropy will either increase or remain constant. In simple terms, entropy naturally tends to rise and never decreases on its own. Watching how things move toward greater chaos around us helps us see the one-way flow of time. Picture a deck of cards arranged neatly. If we shuffle them, this change causes them to become disorderly. The transition from order to chaos is an illustration of the unidirectional nature of time, as seen in everyday occurrences like melting ice or stirring a cup of coffee. Back in the late 1980s, these simulations revealed something really interesting about Pluto's path. Even though it has factors like U-libration and latitude libration to keep it steady, its orbit can still be quite wild and baffling. If you start off with just a tiny difference in Pluto's position or velocity, its path may ultimately look drastically different. But even with all this chaos, Pluto's orbit remains stable for an extremely long time. Pluto has been around for billions of years, and its journey around the Sun follows a certain order, even though it may seem all over the place at first. Predicting cosmic occurrences, particularly when they involve chaotic orbits like Pluto's, poses significant challenges. The inherent unpredictability of these systems means that long-term forecasts are often fraught with uncertainties. While numerical simulations provide a powerful means to understand and anticipate the future paths of celestial bodies, they also highlight our predictive limitations. These models rely heavily on the accuracy of initial conditions and the intricate nature of the interactions they simulate. Any minor error or oversimplification can lead to vastly different outcomes, making precise predictions a difficult task. The chaotic nature of celestial orbits like Pluto's serves as a reminder of the ever-dynamic and changing nature of the universe. While we have made significant strides in understanding space, the case of Pluto reminds us that our knowledge of the universe still remains limited. Understanding the gravitational effects of the enormous planets that orbit Pluto provides useful information about the broader dynamics of the solar system. It shows how the presence and position of each planet can have far-reaching effects on the stability and trajectory of other bodies within the system. So why are major astrophysicists only now raising concerns about a possible collision between Pluto and Neptune? Despite all these complex forces working to prevent such an event, prominent astronomer Neil deGrasse Tyson, who played a key role in popularizing astronomy, provides a unique perspective on the mysteries of our solar system, particularly the intriguing case of Pluto. Tyson, known for his role in Pluto's reclassification from a planet to a dwarf planet, offers insightful analysis on the changing nature of celestial mechanics and the public's fascination with the unknown realms of space. He views Pluto's reclassification not as a demotion, but as a necessary adaptation to our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is an ongoing process of learning and adaptation. He sees the complexity of orbits like Pluto's as a reminder of how much there is still to discover about space. In light of these unknowns, particularly the potential interactions between Pluto and Neptune, he highlights the dynamic and unpredictable nature of our solar system. His work emphasizes that the more we uncover about space, the more questions arise, pushing us to explore further and refine our understanding of the cosmos. Michio Kaku, another renowned physicist and futurist, offers a complementary perspective on the mysteries of space, focusing on the often unpredictable forces that shape our universe. Kaku is known for his ability to bridge complex scientific concepts with futuristic visions, making him a significant voice in discussions about celestial mechanics and their broader implications for humanity. Kaku's views on Pluto and its orbit emphasize the need for continuous observation and advanced modeling to understand and prepare for potential cosmic events. He sees the interactions between celestial bodies as a crucial area of study, not just for academic curiosity, but for practical implications. The potential collision between Pluto and Neptune, for instance, is not just a theoretical scenario but a reminder of the dynamic and often chaotic nature of space. Kaku's futurist outlook pushes us to consider the broader implications of such events, from their effect on our understanding of the solar system to the potential need for future space interventions. His perspective underscores the importance of being prepared for the unexpected. His work suggests that the more we understand the forces at play, the better equipped we will be to navigate and potentially mitigate the effects of cosmic events. Both Tyson and Kaku share a consensus view that space is a realm of never-ending discovery, and that our current understanding, while vast, is still limited. Their emphasis on continuous exploration and advanced modeling reflects the evolving nature of space science. They stress the importance of not just understanding celestial mechanics as they are now, but also anticipating how they might change in the future. The potential collision scenario between Pluto and Neptune serves as a case study for the broader challenges and opportunities in space exploration. It underscores the need for robust scientific inquiry, advanced technology, and a willingness to adapt our understanding as new information emerges. Tyson and Kaku's work in uncovering the mysteries of space, exemplified by Pluto's orbit, is a call to action for the scientific community and humanity at large to keep expanding the scope of our knowledge. There is a general scientific consensus that, for the foreseeable future, Pluto and Neptune's orbits will remain stable due to their mean motion resonance and the various gravitational influences acting on them. Therefore, a direct collision between Pluto and Neptune is highly unlikely. However, the complexities and potential perturbations in orbital dynamics mean that astronomers must continue to monitor and study these celestial bodies to better understand their long-term behaviors and any potential risks they might pose. While the scenario of a Pluto-Neptune collision is largely speculative and considered improbable based on current knowledge, it highlights the importance of continuous research and observation in astronomy. Advances in technology, including improved telescopes and computer simulations, will help astronomers refine their models and predictions, ensuring that we stay informed about the dynamic and ever-changing nature of our solar system. Tyson's perspective on Pluto's reclassification and Kaku's emphasis on the unpredictability of celestial mechanics both underscore the need for continuous exploration and a flexible understanding of our universe. The potential collision scenario, while speculative, highlights the dynamic and complex interactions within our solar system. Ultimately, it reminds us of the vast, still uncharted territories in our understanding of space. Through ongoing research and observation, we strive to unravel these mysteries, ensuring that our knowledge keeps pace with the ever-evolving cosmos.